Area between curves using horizontal rectangles. Our objectives are to demonstrate how to calculate the area between curves when using horizontal rectangles and to compare the use of vertical bars with horizontal bars when determining the area between curves. Some materials for review include definite integral calculations, graphing, and determining intersection points between functions. We'll begin with the process if graphs cross, just as a reminder. The graph the two functions on the same set of axes to start with. If an intersection point occurs within the closed interval you are considering for integration, find these intersection points by solving f of y equals g of y. Use the additive property of integrals to rewrite the definite integral from a to b of f of y minus g of y dy and split it apart into two integrals, where you have the integral from a to c of f of y minus g of y dy. And over this interval a to c, this is where f of y is greater than or equal to g of y. Then you're going to add to it the definite integral from c to b of g of y minus f of y. And then over this interval is where g of y is greater than or equal to f of y. And of course, c is the y coordinate of the solution between f of y and g of y. Evaluate each integral to obtain the total area between the curves. So our example that we start with here is we're going to suppose we wish to determine the area between the curves x equals 3 minus y squared and x equal y plus 1. First, we're going to approach this naively using vertical bars. So when I graph these two functions, I have solve for y, and I have y is equal to x minus 1, and y is equal to the square root of 3 minus x. So here we can see two vertical bars to demonstrate our orientation. We have intersection points between -1 and -2, and then 2, 1. These are the intersection points between those two graphs. And since we're using vertical bars, the x coordinates will form our interval of integration. Before jumping into the integral, we take note that the curve x equal to 3 minus y squared bends back on itself. So when we solve for y, we're going to need y is equal to plus and minus square root 3 minus x. And examining the graph shows us that from x equal 2 to x equal 3, the upper curve will be y equals square root of 3 minus x. The lower curve will be y equals negative square root 3 minus x. From x equal -1 to 2, the upper curve will be y equal x minus 1, and the lower curve will be y is equal to negative square root 3 minus x. So let's review the graphs a little bit so we can see where these notes are coming from. From -1 to 2, where this kind of red line is drawn here, this is where the graph of y equal x minus 1 has larger y values than the graph of y equal the square root of 3 minus x, or y equal the negative square root of 3 minus x. So here, all the way up to this point here where x is 2, we have y equal x minus 1 strictly greater than y equal negative square root 3 minus x. But from beyond this point x equal 2, it is now the curve that y equals square root of 3 minus x that is above the curve y equal negative square root of 3 minus x. So we're still going to have two separate integrals to evaluate. We have the integral from -1 to 2, where we have y equal x minus 1, minusing the negative square root of 3 minus x. But once we get past the point x equal 2, we now need to change our functions that we're subtracting to y equals square root of 3 minus x, and then y equal negative square root of 3 minus x to get the area between those two curves. And again, notice the intersection points of the curves do not correspond to the interval of integration in this case. The interval of integration is -1 to 3. In this situation, the two integrals that will be needed are the integral from -1 to 2. We have y equal x plus 1 as the upper function, and again, y equal negative square root of 3 minus x as the lower function. And from 2 to 3, we have y equal the positive square root of 3 minus x as the upper function, and y equal negative square root of 3 minus x as the lower function. So here are the details of evaluating the area between those curves over the respective regions, and we get our final result of -9/2. Our second example, we're going to consider the same problem, except this time we're going to use horizontal bars. So we're going to rotate our thinking so that y is now the independent variable and x is the dependent variable. So here we're going to integrate with respect to y. So now we're looking over the y interval where one curve is above the other. So it's kind of like rotating the picture counterclockwise 90 degrees. And using this, we only have one integral to evaluate because the upper function will always be the upper function over the interval of integration. There's no intersection points over our interval. And then another advantage in this case is that the intersection points correspond to the endpoints of the interval of integration. So if you don't do the rotation, the curve further to the right will be considered the upper function, and the curve further left will be considered the lower function. And in this case, our integral goes from -2 to 1. These are the y values now, not the x values. And when we run through the details of this integration, we again get 9/2, which is good because the area shouldn't change because I changed variables. But going back to the picture, we start from -2, we go to +1. Remember, this is the y coordinates that are now the integral that we're interested in with the y coordinates. And we can see here that the 3 minus y squared graph is always above the line y plus 1. So in this particular instance, the integration was much, much easier to perform. And sometimes it does require that we do a little bit of change of variables and change of perception in order to make the algebra work easier. Some last notes. Integrating with respect to y in this case proved to be less arithmetic work. And again, this demonstrates the importance of graphing the functions before performing calculations. One perception may lead to easier calculations than the other, just like it did in this case. Now, there's nothing that says you can't integrate with respect to x, but as we saw with just this simple example, the calculations can become very daunting very quickly. So please remember, graph your functions, and then make a decision as to which one you think is going to be easier to integrate arithmetically. Thank you for your time and attention.